Okay, we're recording. Okay, so we're going to talk a little bit more about integrals and some applications of integrals. I'm going to start with what I think is one of the most underappreciated tools for computing integrals that I'm aware of. It may be the most underappreciated. Symmetry theorems. Now, I suspect y'all have probably seen the following in single variable calculus class. If you're looking at an integral like this, and now specifically, if your integrand is what we call odd, right? So f of negative x is negative f of x. So odd powers of x, for example, I have this feature. And notice that our domain is from negative a to a. This is what we call symmetric, because it's like it is its own reflection over the origin. If you flip everything over the origin, nothing happens, right? When this happens, your integral is equal to 0. Drop the pen, walk away, right? Pretty neato. Gotta love it. I didn't have to take an antiderivative. It's awesome, right? I mean, antiderivatives can get pretty hard sometimes, and so not having to take any antiderivative is pretty awesome. Okay, so what we want to do is we want to develop a multivariable version of this idea, this extremely powerful idea, and it's arguably even more powerful in 2 and 3 dimensions. So first of all, let's talk about why it's true. The big idea is I'm going to take a Riemann sum point of view on this, given where we are in the course, and I'm going to be looking at a graph. Now, I emphasize that's again not to be assumed, right? But let's go ahead and look at the graph in this case. And the terms in the Riemann sum, well, you got a bunch of terms that various things that you're adding up there, right? And in particular now, I want to look at 2 of those terms. We'll look at this term right here, where it's negative x is the sort of the x value for that term, if you will. And then I want to look at this term over here, where x is the x coordinate that we're looking at, right? Okay, well, here's the deal. The value of the function on the left and the value of the function on the right, by design, are exact negatives of each other. The delta x's that we're multiplying by to get the terms in the Riemann sum are, of course, equal. And that means that these 2 terms are exact negatives of each other. Exactly negatives of each other. And so in the Riemann sum, they cancel. Does that make sense to everybody? Yeah. And then likewise all the other terms. Now, so what's the symmetry got to do with it? We see where the oddness comes in. The oddness is what makes this minus sign come up. The symmetry comes in the fact that I need these terms to pair up, and everybody's got a buddy, right? X goes to negative x, so these 2 terms cancel. And then I can go a little further out to, let's say, I don't know, there, and then it's got a buddy over here, and those terms cancel. And it is only from the fact that this is a symmetric domain that where you run out on the right and where you run out on the left are the same. And so you don't have any leftover terms remaining after you cancel, right? So that's why you need both of these conditions. The function's got to be odd for the cancellation to happen in the first place, and the domain's got to be symmetric so that the cancellation will leave nothing left over. Okay, so those are our 2 conditions. So let's talk, how would I do a multivariable version of this? It's going to all start with this idea of a reflection through a line. So let's I can do better than this. Let's suppose we have a line here called L, and reflection means exactly what you think it means. Right? So now how we define this precisely, we could say, given a point x, the reflection is the point that makes this line segment perpendicularly bisected by the original line. So if you want to be precise about it, yeah, sure, we can do that. But I prefer to say it's exactly what you think it is. Right? And the how you write down a formula for this reflection is going to depend very heavily on the picture. And we'll talk through some examples of that in a few minutes. But for the moment, let's just talk about, in the abstract, this idea of a reflection. And a couple of related ideas. What would be the version of oddness that I would associate to this reflection? Well, the idea is that if I look at, let's see here, let me get back into pencil mode here. If I look at a point, and if I look at its reflected point, a function is odd if when you do, let me try to be consistent here. Reflected point. A function is odd if by the act of reflection you get a minus sign on the value of the function. And I claim that this is, if you think about it, this is totally analogous to the idea of oddness that we talked about for single variable functions, right? It's just that you can really only reflect over a point if you're just stuck on the number line. There's not enough sort of room you can't reflect over a line, there are no lines, right? So now that we're in 2 dimensions, it opens up a lot of possibilities for different ways to reflect, and so this is our generalization here. Okay, another idea. What do we mean by a symmetric domain? And this one, again, I'm going to kind of borrow from the previous page. I'm going to say a domain is symmetric if it is its own reflection. Said differently, whenever you have a point that's in the original region, the reflection is also in that same region. So, again, just kind of borrowing the idea. Let's see, I think I have a picture here somewhere. Yeah, here we go. So this, for example, this shape here, kind of a weird shape, but I argue that is symmetric over this line, because if I look at a point, this point here, for example, if I were to reflect through the line, that gives me this point here also in the set. And I argue that it is exactly the fact that this is what you're going to want to call a symmetric shape, symmetric over that line in particular, that makes this property work. The fact that that these always come together is because of the symmetry. Is that geometrically satisfying? Okay. All right. Okay, so a big theorem, and I'm not going to exactly prove this. I'm just going to do some kind of hand waving about it, but it's totally analogous to the single variable version we just saw. If you're looking at an integral, if that integrand has odd symmetry, and if your domain is symmetric, then your integral is equal to 0. Drop your pen, walk away. Totally awesome. Super awesome. Not only did I not have to do an antiderivative, I didn't have to do the second antiderivative that I would have had to do after I did the first one, right? And I also don't have to go through that chopping, slicing, and dicing process, finding bounds and all that business. I can just, quick observations and boom, declare victory. Yeah.
What does the D refer to here again?
One more time.
What does the D refer to again?
The domain for the integral. Yeah. Is that cool?
Yeah.
Okay. Now, couple of asterisks. You do need both of these conditions. This is extremely important, and this is one of the most common mistakes that students make when they're talking about symmetry. Is they notice, for example, a student might notice, I see my domain is symmetric. That must mean my integral is 0. Nope. It's not good enough. The domain being symmetric by itself does not tell you anything. Likewise, sometimes students see an integrand that has like an odd power of x. Oh my gosh, I can see it coming. This is going to be an odd function. Yeah, but you don't forget, you got to look at the domain also, right? It's very, very important. So again, I'm going to sort of highlight here. You need both of the conditions to apply. Second, and another really nasty little landmine that a lot of students can accidentally step on, and that is, it's got to be the same line. Same line for both of the conditions. It is absolutely not good enough for your integrand to be odd over one line and your domain to be symmetric over different line. The argument just crashes and burns. It just doesn't work. And we're going to see some counterexamples of this. Okay, so anyway, heads up for those two landmines. Really, really dangerous. And just from a grading point of view, exam, practical point of view in that sense. Let's suppose that you have an integral to compute on an exam, and you accidentally step on one of these landmines. Then what you're going to effectively write on the paper is this integral equals 0 by symmetry. But the sad truth is the integral is probably not even equal to 0, and it's certainly not susceptible to a symmetry argument. So nothing written on the page is both true and relevant to an actual solution of the problem. And that puts a grader in a really tough situation. Right? Well, what do you do? There's nothing to give points for. Nothing's right. Does everybody see that, how nasty of a problem that is? So as much as I love this theorem, and I do, it's awesome, right? Careful. Be very, very careful. Double check it. Think it through. Don't race the clock. It's already going to save you a bunch of time, right? But make sure to check that you have thought through both of these conditions, and make sure that you're using the same line for both of them. Okay. All right. So, real quick argument as to, again, why it works, just kind of thinking it through. And we've already kind of made this argument. This is just a repetition. But I can think about this little piece in the Riemann sum, if I were doing a double integral over this, lumpy shape. On that term, right, value of the function times area, term in the Riemann sum. Now looking at this little term in the Riemann sum over here corresponding to that chunk, and that gives me, again, value of the function at that point times the area. That's another term in the Riemann sum. And notice that because of the oddness, these are negatives of each other, and therefore they cancel. And because of the symmetry, every term similarly cancels with its sort of buddy sort of reflection piece over the line, and so there's nothing left after all the cancellation, and so we get 0. So totally analogous to what we saw in single variable, just kind of two-dimensional version. Yeah.
You know how in single variable you say odd if only if symmetric over origin?
Yes.
This I assume you can choose it.
Yeah, that's right. That is one of the big advantages here is that you have more options, and so you'll notice that what I put in the quotes here, the term is not odd. The term is odd over a line, so you have to specify the line. So good news, yeah, you got options. Bad news is you got to specify. Does that make sense to everybody? Great question. Okay. Alrighty. So let's see an example. Suppose I need to compute this integral right here. So it's an integral. We've got a domain given. We've got an integrand given. So specifically my domain is the unit square. And my integrand is this function right here, x minus y. Now, that's not even a hard integral, right? We could totally do that. But let's just exercise our new muscle here, use our new tool. Let's try to make a symmetry argument. First thing to notice, this square is symmetric over a lot of lines, if I could draw competently. Right, bunch of different lines over which the square is symmetric. So we can't just say the domain's symmetric. It's not good enough. Right? You got to, what kind of symmetry do we have? Specifically over what line, because we've got to double check and make sure that line's the same line we use for oddness. Right? So I'm going to start with the right answer here, which is that we're going to use, if I can draw competently, close enough, there's the line that we're going to use, the line y equals x, for which I argue that this is the formula for the reflection. Now, this is a geometry argument that you've got to kind of think through. But if you give me a point x comma y and flip it over that line, the x becomes the y becomes the x. If you don't like that argument, then let me draw a little picture here. If I think about this point, start it in green. That point has an x coordinate, and it has a y coordinate. And now let's ask, not just what happens when I reflect that point, but what happens when I reflect this entire little picture that I've got here. I'm going to reflect the orange little line segment and the purple line segment and the point that motivated them. Well, when I reflect that entire thing, the orange is going to turn into something like that, and the purple is going to turn into something like this. And so this blue point, the reflection, is that given this green point, xy. Everybody see it? In other words, what had been the x coordinate becomes the y coordinate, just because of the nature of that reflection. So now that's a geometry argument. You're going to have a different geometry argument every time. Every time you come up with a new line that you want to do a reflection over, you get a different formula. Okay. All right. Now that said, first, is the domain symmetric over this line? Why, yes, it is. Casual inspection, geometrically obvious. You don't really have to prove that. In cases when it's true, it's usually pretty clear. So that's fine. That said, you do have to say it, right? It is a critical part of the argument to recognize that the domain's symmetric. All right. So now, let's talk about oddness. Is this function odd? It's tempting to look at this formula and say, well, I do happen to see only odd powers, but that's not the definition of oddness. What I actually need is to take this reflection here, this act of reflecting, that reflection right there, right? I've got to ask what happens when I plug in that reflection into the function, and does the value of the function go negative? I've got to compute, and I've got to make sure that I end up with exactly the negative of the value that I started with, right? So this calculation, you got to actually sort of lay it out there. So in this case, what we can do is say that I need to evaluate f of y comma x. So the first coordinate that I plug in wherever I see an x is y. Right? And then the second coordinate that I plug in wherever I see a y is x. And so f of y comma x is y minus x. Does everybody see that? It's a little uncomfortable because the x becomes the y and the y becomes... you can see that there's a confusion issue there. An alternative, if you prefer, is to change your formula to talking about reflections of points s comma t. Right? And then rewrite this whole thing in terms of s's and t's. Right, and then you don't have a confusion of variables. And if that is more comfortable, more satisfying, then you can totally do that as well. Okay. All right. Okay, so in this particular algebra, notice we ended with y minus x. Thankfully, that actually is exactly the negative of the x minus y that I started with. So I do indeed get this minus sign that I needed, and sure enough, then this function is odd. Everybody happy? And now we just declare victory. It's spike the football. Odd function, symmetric domain, integral 0. Yes, sir. Oh, yeah, that's right. Well, so I'm not going to prove this. I'm just going to make a geometric hand-waving argument, but that line is kind of the 45-degree line, and this being the unit square. So the idea, and again, you don't have to prove this. You just have to state it, and you have to be correct, right? But if you think about it, this point reflects to that point, right? And this point just stays where it was, and that point stays where it was, and this point, of course, reflects back to that point. And then it just kind of... Yeah. That's the idea. So that's the definition, right? You go back to the definition. It's symmetric if whenever you have a point in the domain, the reflection is also in the domain. Yeah. So, and again, I don't want to get bogged into the formalities of proving that, because that's notation and formalities. And it's, like I say, it's usually pretty obvious. And if I were to just make the geometric case that, this square is symmetric over that line, I think it's geometrically comfortable. You see what I'm saying? And that's good enough. Okay, let's see another example. This one would be a harder one, hypothetically, if not for the fact that it was going to be zero by symmetry. But it could. But this is one where it actually would be somewhat of an effort to actually crank this out, because on the one hand, look at the integrand. The integrand's a little uglier. Secondly, look at the domain. The domain is not a rectangle. The domain is now a triangle, which means the bounds are going to be formulas, and thankfully, at least they're still straight lines, right? But still, there's going to this could get a little annoying. Not that bad, but still. So, the points that I'm given define this triangle, and again, I'm just going to appeal to your intuition. Symmetric over the y-axis. Is that cool? Right. Okay. So the domain is symmetric over that axis. What about the function? Is the function odd? Well, for the function to be odd, I'd need to understand this reflection. That's what the reflection looks like. Notice that reflection puts a minus sign on the first coordinate. Again, that's just what that reflection does. Every reflection's got a different formula. Reflecting over an axis is very convenient, because you just think about, well, only one of the coordinates is going to go negative, or the negative of what it had been, and the picture will just tell you. But you do have to think it through. Nasty little fact here. A lot of students get confused over this. Notice that even though it's the y-axis, it's the x coordinate that gets the minus sign. That trips up a lot of students. So please don't rely on symbolic arguments, memory, like that. Please think through the picture every time, because it's not a hard picture, and the picture will always lead you the right way. Does that make sense? Okay. All right. And so, let's check and see if that function is odd. And here we go. What I'm going to do with the reflection puts this minus sign on the x coordinate. So I've got to ask now, what happens when I take minus x and plug it into my function? Well, I get minus x cubed instead of x cubed. Nothing happens to y. Y is still y. Colors. Y is still y and plugs into y and remains y. Nothing happened there. Again, lucky, convenient reflection. That's just the way that one works out. And so now, again, you got a little bit of algebra to do. You got to figure out what this is, and is this the negative of what the original function was? And, well, yeah, it is, because the original function here is x cubed e to the y, and we're looking at negative x cubed e to the y, and so there's that minus sign that gives us the oddness. I should have written the word odd somewhere here, but anyway, the function's odd. So, we're done. This integral is zero by symmetry. Everybody happy? Okay. All right, so super cool. This is a powerful theorem. Nevertheless, it remains that this is a class about reasoning. Right? And so when you invoke this theorem, I do need you to actually give me all of the steps in the process. So going back to our first example here, just for convenience, you've got to tell me what is the line that you're going to make a symmetry argument over. You got to indicate the formula for the reflection. You've got to state and be correct that the domain is symmetric over that line. Now, again, I don't require proof. Well, that's usually, again, pretty geometrically clear, vast majority. So that's fine. But you do have to state it, and you do have to be correct. You can't just claim something symmetric that isn't symmetric. No fair, right? And then you've got to state and prove that the integrand is odd. Now, once you've done these 5 things, then you can just declare victory. Integral is equal to 0, and walk away and celebrate the fact that you didn't have to do any anti-differentiation and etc. Does that make sense to everybody? Okay. All right. Now, I've stated before that you got to be careful with landmines. You got to watch out. Really easy to mess up. So let's suppose that we were doing an integral over this same domain, right? And the integrand, let's suppose, was this function right here. A lot of students, oh gosh, and it's such a tragedy every time I see this, but it's really easy to get too excited. You see daylight at the end of the tunnel, you run for the daylight, right? And then you step on the landmine, right? So you got to be really careful and make sure that you check through everything. You do see this 3 here. That does make you think that this is an odd function. And it kind of is odd. It's just that it's only odd over the x-axis. Whereas this domain here is symmetric only over the y-axis. So there is no argument over the y-axis because the function's not odd. There is no argument over the x-axis because the domain is not symmetric over the x-axis. And so there is no symmetry argument to be made, right? If you try to make a symmetry argument, it's nonsense. Absolute nonsense. Does that make sense to everybody? So, again, it's a powerful but dangerous tool. By the way, here's another sort of obvious, if you look at this function right here and think about what that function does in this domain, notice that in that domain, y is clearly always positive. That means that this factor is always positive. Then you can look at this factor here. That's a square. That's never negative. So I'm just going to say that's always positive. So on the domain in question, my integrand is never negative. There's no symmetry argument when your integrand's never negative. You need cancellation, right, for a symmetry argument to work. So not only does the symmetry argument not work, it's not a matter of formalities. It's that it's really, really not symmetric, very importantly. So it's, again, a symmetry argument is just absolute nonsense here. Okay. All right. So, good stuff. Let's talk about some physics applications. This is not a physics class, but there are various physics problems that are really good excuses to write down applications of double integrals that are useful. And some of y'all are physics majors, engineers, things like that. Chemists will use these kinds of arguments as well. So, okay, first I want to talk about this idea of torque. No big deal. Again, this is not a physics class, but the very broad stroke, short version of what torque is it's kind of a rotational version of force. Force is where you're pushing in a straight line. Torque is where you're turning around an axis at an angle, right? So if you're tightening a screw in a screw hole, that's, you have to apply torque to get it to go through the hole. So roughly speaking, it's kind of like force. Is everybody willing to kind of buy that? Okay. All right. So I don't know if any of y'all have ever changed a flat tire on the side of the road. That may be kind of a thing of the past. But I have. And I can tell you one thing very much for sure, and that is that if you try to take a lug nut and grab it with your fingers and turn, it's not going to turn. Forget about it. And the reason why there is because the distance from where you're holding it to the axis that it's turning around is like half an inch or something, and that's not very much of a distance. Whereas if you get a what do they call those? The tire iron. Thank you. And then part of it plugs into the lug nut there, and then there's an arm that comes out that's usually about 1.5 feet long. And then when you push down on that, well, you can apply massive, massive torque because that longer arm makes it a lot easier to turn it. Kind of plausible? Everybody buy that? Okay. And then another thing you can do, and I used to do this, is carry around what they call a cheater bar. And that's in cases where, this is a total tangent, but if you get your tires replaced and they use an air gun to put the lug nuts on, they're on really tight. And then even the tire iron, you try as you might, put your whole body weight to stand up on top of it, jump down. You just still can't get it to move because it's on there too tight. So a cheater bar is when you just go to Home Depot and buy a 4-foot length of iron pipe and just carry that around in your trunk. And then that you can put over the tire iron, and now you've got something this long. Now you're good. And that's been handy for me in the past. Okay, anyway. So here's the big idea. If you are rotating around a point that I'm going to call S, and let's suppose that you're talking about a little piece of mass there that's going to be pushing down with a certain amount of force, like that, right? Then this is how long your lever arm is, and the amount of mass that it's pushing down with, or the amount of force that it's pushing down with, is proportional to mass. And so we can talk about how much torque there is provided by this point. The amount of torque is just, it's going to be proportional to the length of the lever arm, and it's going to be proportional to how much weight, namely how much mass, let's not worry about units, is at that point. So there's a formula for how much torque there is at this one little point. Now, harder question. What is the total amount of torque over the entire rod? Right, I've got this one-dimensional metal rod here, and this little piece of mass is providing that amount of torque, but there's a bunch of other little pieces of mass. And so, I just add those up. You add up all of the individual little pieces of torque to get the grand total torque that this metal rod applies around the axis or point of support, right there where you're holding it up. Okay. Fine, who cares? Here's a nice little application of this, and that is to say, what if I wanted to balance it? And I'm going to use my pen instead of my stylus because the stylus is expensive. And if I drop it, I don't want to have to pay for a new one. Pens are cheap. Okay. So look, so this is called the balance point on the pen because the pen is balanced right now. If I were to hold it instead here, there's going to be more torque going down that way than there is this little tiny little bit of pen over here doesn't apply much torque the other way. So here, the total torque is not 0 and the thing falls. But at that support point, the total torque is 0. And that's why it balances. Okay, so if I want to find that balance point, all I have to do is take this torque, set it equal to 0, and then solve for what I'm interested in. In particular, I'm interested in the balance point. The balance point is this point here that makes the torque 0. So we're going to solve for S. And notice I can take this integral, separate it into two terms. The S, of course, is a constant because the whole idea is that it's supposed to be a fixed point that doesn't move. So being S is a constant, it factors outside of the integral, and you can solve for S really easily then, and there it is. So this is called the centroid, sometimes called the center of mass, and the typical notation for this is to call it X bar. The idea there is that this is now this is a different point of view, and I don't want to digress on this, but This bar here typically means an average. So in a sense, this is an average of all of the x coordinates. It's just that it's an average that's weighted by where the mass is. And so this is overall what's called a weighted average. Anyway, bar as a sort of a hat on top of a variable typically means some sort of an average. Okay. All right. So what if we had a two-dimensional region? And there's going to be a point of support on that two-dimensional region. And you could make arguments totally analogous to what we just did, asking first if I wanted to support that mass, that two-dimensional region of mass, if I wanted to support it with a line. I could ask first, where is that line in the sort of the x direction? Right? Obviously this isn't going to work. Obviously that's not going to work, but somewhere in the middle. Right? And then likewise, you can ask where is that line kind of in the y direction? And again, there's obviously only going to work with one y coordinate. So there's an x coordinate, there's a y coordinate that make it balanced, and the intersection of those two lines is going to be the single point support, which now I might not be able to do. Oh my gosh, I got it. Look at that. What are the odds? So that single point that supports the whole thing. Does everybody buy it? So the results of those arguments are right here. So this is called the x coordinate of the centroid, and this is called the y coordinate of the centroid. Okay. Now, real quick, little detail. Sometimes we're thinking about a piece of mass. Mass has density. Sometimes, though, we're just thinking about just the geometric figure itself, and we don't want to worry about mass. It's not a physical thing. It's just a geometric thing for whatever reason. Some reasons are going to come up in a few minutes. But in that case, if you're interested only in the shape, if there's no mention of mass, just assume the density is 1 and same arguments. Makes sense. Okay. All right. So here we go. Let's do one. Here is the upper semi-disk. And that's an area and a radius A, density 1. So in other words, we're not going to worry about density. And let's find the coordinates, the centroid. Where's the point of support? Okay, well, we have formulas. These are the formulas. Keep in mind density is 1, so mass here is just area, because there is no density. If mass is area, well, the area of this is pretty easy to write down. That area is just, whoa, okay, well, I missed the thing. But anyway, area is, it's half of a disk of radius A, so that's no problem. Then these are just, this is what the formulas look like. Just directly above. And we have two things to compute. Now, good news on the computations. This one here, 0 by symmetry. Gotta love it when that happens. By the way, this happens a lot. I like to point this out because I think it's persuasive. So in my undergraduate days, I did a second major in physics, and I did a lot of integrals. Those of you who are engineers are going to be doing a lot of integrals over your time. So my estimate, just based on my memory, just how often did I get to do use which tools, and my kind of sense. It was a long time ago, to be fair, right? But I think about 20% of the integrals that I encountered in my undergraduate physics major. That was 9 courses of physics. 9 courses, chock full of integrals, and 20% of them were 0 by symmetry. Almost 2 entire physics classes worth of integrals. 0 by symmetry. It's a powerful tool, right? And a lot of books barely mention it. This is a hugely important, hugely useful fact. So anyway, please be on the lookout for it. Little stuff like this, like what I've done here, that integral 0 by symmetry. Now you do have to supply the details, right? Again, there's 5 specific details. You got to indicate what's the line that you're arguing symmetry over. You have to notice that the shape is symmetric over that. Blah blah blah. So supply the details, but it's way better than having to crank out that integral. Okay, this one here. No symmetry argument. It's not possible. Try to find a line that satisfies the required conditions. There is no such line. This is, again, you got to watch out for the landmine. You could totally imagine that students would look at this and think, oh, that's an odd power, and my domain's clearly symmetric, and boom, 0, and that's just all 100% wrong. Nothing right, all wrong. So heads up, be careful, please don't step on that landmine. To compute this integral, you have to actually crank it out. Now, you do have a choice, and that is in which way you slice. Here I've done dx dy. That makes the bounds look like this, and the integral looks like that, and it gets you down to an answer. Fine. Your other option would be to do it dy dx. Same integral. Bounds look like this, and you crank it out, and the answer, and now you get the same thing either way, right? Well, you better. We're computing the same integral. You better get the same answer. But I just want to point out that you get to decide for yourself which one of these calculations you'd rather do. And I have a preference myself between these two options. And one thing you can do and just try to gauge pencil lead, which one of these has the most pencil lead on the page. But I'm going to point out furthermore that if you look at this one here, you look at your integrand y here, and you look at what you're about to plug into whatever the antiderivative ends up being, you're going to have to plug in a square root into whatever the antiderivative ends up being, and I don't like square roots. In fact, I really don't like square roots, and that square root, if it remains, is going to be part of my integrand for my x integral. I really don't want to have to do an integral that has square roots in it. Those are at best inconvenient and at worst intractable. So my little hack, right, that I encourage y'all to try to take advantage of is then think strategically, well, hey, this y that I'm going to be integrating, if I were to do the dy integral first between this pairing, that makes me have a square, and when the square root goes into the square, it disappears. And I get a much nicer integrand. Now that was a kind of a little strategic little hack, right? I chose the order of my slicing so that the integration would work out a certain way. Sometimes that's a useful point of view. Everybody buy it? Okay. All right. Okay, theorem of Pappus. My speculation is that the reason that this awkward phrasing, theorem of Pappus, is so popular is because nobody wants to venture out into how to make Pappus possessive. Is it Pappuses with the apostrophe, or is it apostrophe S, or, you know? And it's just, we stop that argument entirely by just saying theorem of, and, ignore the issue entirely. Okay, so it's a really clever idea. It goes like this. Suppose you have a plane, and you have an area in that plane, and then you have a line also in that plane, and very importantly though, I need all of the area to be on entirely one side of the line. The line is not allowed to cut through the middle of the area. Okay, so here's our picture. Is everybody on board with the picture? Now, I could then ask the question, what happens if I take that area and if I rotate that area around the line, that generates a volume. And what we're going to try to do is understand a relationship between the area and the volume that it generates. Everybody see the kind of the problem? Now, real quick, I want to point out this line that I've got here. I drew it at kind of a weird angle. I did that on purpose. I want the argument that we're going to make here to be a general argument. I don't want it to apply exclusively to if you're rotating around the x-axis or exclusively the y-axis, or in fact, it doesn't even have to be an axis at all. Right? So I'm going to draw it at a weird angle, and that's going to make the algebra that we're about to write down look a little unrelatable. But in practice, day in and day out, these lines tend to be either the x-axis or the y-axis, or a line parallel to either the x or the y-axis. In which case, everything's going to work out very nicely. Okay. All right. So that said, here is the argument I want to make. Whoops. I want to come back up here real quick. The total volume, I argue, I can think of as being what I get when I take each little piece of area and rotate each little piece of area separately. Now, this is a hard picture to draw, so I'm not even going to try to draw it, but I'm just going to appeal to your intuition. This area that I'm rotating to generate the volume, that area consists of a bunch of little pieces. When you rotate those pieces, they don't trample over each other. So it's like I'm going to take this rotated volume and kind of slice it circularly or something, right? I'm going to turn this entire thing into a bunch of rubber bands, right? And that the total volume is just the sum of the volumes of each one of those little kind of rubber band shaped things. Is that plausible? All right. So what I'm going to do is I'm going to write down a formula for the volume generated by one little piece of area, and then I'm going to add that up over the entire region, aka I'm going to turn that into a double integral. So here's that process. First little piece of area, and that generates this volume. And I argue that that volume is equal to the area itself times this kind of length, if you will. If you were to imagine this again, this being a rubber band, if you were to snip that rubber band in one spot and just kind of straighten it out, don't stretch it, right? But just kind of lay it out straight, it would be a little rectangular box, and this is basically area times length for a rectangular box. Is that plausible? Okay. And of course that length is the circumference of that circle, which is 2 pi r, where r is the distance from that point to the axis. And now that's where things start to get a little creepy looking, because you're like, oh, wait a minute, how do I compute that distance to that axis? And don't I need to worry about that? And here's the good news. Again, the axis is usually going to be either perfectly vertical or perfectly horizontal, and that it's not going to be hard. I'm calling it r instead of x or y because I want to keep it general. That's all. Right. Okay. Okay. That said, okay, so we've computed a volume here, this volume of one little piece. And now I got to add that up over the entire region. And so that's the integral part of this. And so we have an integral representing that volume, and you could totally compute with this, and that's totally fine, but there's a really slick move to be pulled here, and what makes this Pappus's theorem is we're going to take that, and then we're going to multiply and divide by the area for reasons that'll become clear in a moment. But notice that's all that's really happened here. I mean, I guess I did take this 2 pi and factor it out, right? But other than that, nothing's really happened. And yet, check out this expression right here. that looks just like the formula for the center of mass, aka centroid. And in particular, this is the distance, because you notice the distances I'm talking about here are r. This is the distance from the center of mass to the axis of rotation. So, awfully convenient. So this gives us a really cool result. I'm going to call this distance to the center of mass, I'm going to call that r bar. And then I'm going to notice that, multiplying it by 2 pi, if I have a radius and I multiply by 2 pi, then I get the distance that one point got rotated. So distance traveled by the centroid, and we have ourselves a pretty awesome formula now for how to compute volume. Volume, sure, you compute that integral if you want, but much better. Volume is just the area that you started with times the distance traveled by the centroid. And if you happen to know the centroid, this is awesome. Let me show you an example of this in action. So let's suppose that we were to take this triangle right here in the XY plane, and if I were to rotate that around this axis over here where x equals 1. And if you were to rotate that around, then, you get this kind of, I'm not going to shade in the whole thing, it would just become a big blob of yellow. But you get this kind of, my best metaphor for this is that it looks like a volcano cone, sort of, if you will. Yeah. So anyway, that volume, how would you compute that volume? Now, you could turn this into a single variable calculus problem, sure. Right? And various different ways. You'll probably remember from Calc 2 classes that you could use a shells method or a washers method and turn this into an integral, and you could crank it out. I'm going to argue much more conveniently that according to Pappus's theorem, I just need to take the area, which is an easy little geometry problem, and multiply by the distance traveled by the centroid, aka 2 pi times the distance from the centroid to the axis of rotation. And look, there's a lot of things I don't know about that centroid. How high that centroid is, oh golly, I don't know. But I do know, perfectly obvious, this being a triangle, an isosceles triangle, in fact, that the centroid's got to be on the y-axis. That's just geometrically clear. And any point on the y-axis, this distance here is just 1. So, area times 2 pi times the distance to the centroid, and our volume, super easy to compute. No integral necessary at all. Everybody see how nice that is? Cool fact. Okay, here's another example. This time I'm going to kind of go the other direction. Previously, what we just did is we used our knowledge of where the centroid is to compute the volume. Now I'm going to go the other way around. I'm going to use our knowledge of volume to help us understand where the centroid is. I mean, an equation works in both directions, right? Equals is equals. Right? So you can use this however you want. So I'm going to make the observation that if we take a semi-disk of radius A, recall we talked about this semi-disk earlier, we went to a bunch of trouble to compute the location of the centroid. Right? If I take that semi-disk and if I then rotate that around, that's going to generate a sphere of radius A, and I know the formula for the volume of a sphere. And I know the formula for the volume, for the area of a semi-disk. Well, then I can just solve directly then for the distance to the centroid. The distance to that centroid, aka the y-coordinate of the centroid in this case. Solve. And look at that. You get the same answer that we got by tedious integration a couple pages back. Everybody with me? Okay. All right. This next part I really do have to gloss over quickly because this involves a kind of integral that we technically haven't talked about yet. But I want to point out the analogy and the plausibility. I think this is reasonable. So this time, instead of having an area rotating to generate a volume, now we're going to talk about a curve of a given length rotating around to generate an area. Everybody see what I'm talking about? See the distinction now? This is not an area sweeping out a volume. This is a length sweeping out an area. Okay, so again, you could ask a reasonable question, is there a relationship between the area that's generated and the original length of the piece of curve? And there is a relationship, and it comes from a totally analogous argument that I'm, again, going to kind of sweep under the rug because we haven't technically dealt with this kind of an integral yet, where we're doing an integral of some function times ds. We will deal with these kinds of integrals. It comes up a little bit later. Anyway, I put it in here just as so you can see how the argument lays out on the page in very, very similar way. You can see that I pull this same little fast one where I multiply and divide, this time by length instead of area. All right? And anyway, you get the analogous result. The swept out area is the length, the original length, times the distance traveled by the centroid. So very, very similar result. And let's see an example of this one. Let's look at this, what we're going to call the upper semicircle. And I emphasize semicircle, not semidisc. We're not interested in an area here. This is a curve. There is no area. So it's really not clear. A lot of students would say, oh, it's basically the same as half a disc, and we already know about half a disc. But no, the half a disc would mean that we were including all of this, which we're not. And all of this that we're not including really affects the centroid a lot because there's area there, right? So this is a fundamentally different question, and we have not yet addressed this question, how to find the centroid of that little piece of wire. What I can notice, though, is that this rotates around to generate a sphere. I know the formula for the area of a sphere. I know the formula for the length of a semicircle. And so then, according to this second version of Pappus's theorem, or second theorem of Pappus, whatever you want to call it, the centroid, its distance to the axis of rotation, in other words, the y-coordinate of that centroid, I can just straight up solve for it in the algebra, and it's that. Everybody okay? All right. Okay. Another physics idea. This is a weird one. It's called moment of inertia. Very often when you do math or physics, you start off with an object of interest that you know you're interested in, and then you compute it. Right? But sometimes, and this happens surprisingly often, that's just not how it goes. Sometimes you're interested in one thing, and you're computing it, and you end up with a result where you look at the formula and think, man, this part of that formula is itself really interesting. I didn't know that this was going to come up. I wasn't interested in this thing in the first place, but just because of how this other question worked out, I see that this thing has to be important. And that's what's going to happen here. So we're going to start off never having even given a thought to the idea of moment of inertia. We're going to be talking about kinetic energy. So now, if you've not taken a physics class before, if you don't know what kinetic energy is, don't worry about it. The idea is energy is, it's a deep question, I suppose, right? But it's the thing that makes cars move, right? It's the thing that makes the lights go on in our house. It's conserved, which is kind of bad news because it means we can't just make it out of nothing, right? But it represents the one way to think of it. It represents the amount of work that it takes to put something into its state of motion. All right. So again, this is the formula, but this is the formula for what we call linear kinetic energy. If your motion is in a straight line. Okay, now here's a harder problem. Let's suppose that we are not moving in a straight line. Let's suppose we are rotating around an axis. And in particular, let's suppose that I have a big blob here. A blob of mass that is rotating around this axis. How would I compute the amount of kinetic energy of that blob? And it's tempting to say, well, yeah, okay, just find the velocity and, blah, blah, blah. But, no pun intended. But this little piece of blob right here only travels that far in rotating around, whereas this little piece of blob over here, travels a much greater distance in, again, one rotation. And that means that unavoidably, that orange piece is moving at a higher speed. So I can't just talk about, well, what's the velocity of the motion? The velocity is different on different places. Does that make sense? Have you ever been on a carousel, like when you were a kid or something? I don't know if they still do that these days, but when you're right near the center, you're twisting, but you're not really moving very fast, right? You get out near the edge and you start to notice, whoa, I'm really moving pretty fast, right? Same phenomenon here. So we kind of have to take this formula and chuck it because it just doesn't apply to this rotation circumstance. So what we're going to do is just like we did before. We're going to look at one little piece at a time. Let's ask how much kinetic energy is in that one little piece. That one little piece has a pretty well-defined distance from the axis. I can talk about its speed pretty straight up. An old geometry formula, by the way, is that the actual velocity is proportional to radius. The relationship being angular velocity. So this right here is like meters per second. This right here is radians per second or degrees per second. Pick your angle of choice. We typically, to avoid unnecessary weird constants, keep it in radians. But it's angle per unit time instead of distance per unit time. Is that cool? So anyway, you can write down the total amount of kinetic energy for this one little piece, because on that one little piece, again, everything is moving at the same velocity, so 1/2 mass speed squared, nothing to it. And now it's just kind of a matter of kind of rewriting things around a little bit. We saw previously that speed is omega times r. And let's see here, I can pull this 1/2 outside of the integral. And then notice that we've got omega squared. Now, here's the thing about a rotation. When you have something that's rotating, different pieces are moving at different speeds, but they're all moving at the same angular speed. Each piece of your solid takes the exact same amount of time to rotate a full turn. Otherwise, it would break up into pieces. Right? So the angular speed is constant, and so that also can factor outside of the interval. So what we find ourselves with then is a formula for rotational kinetic energy. Here it is, and it's shockingly familiar, right? We previously, for linear kinetic energy, we had 1/2 mass speed squared, velocity if you like, 1/2 mass velocity squared. Now check out this formula. Now we've got 1/2 times, we'll come back and talk about this in a second, and again, times a velocity squared. It's just that now it's angular velocity instead of linear velocity. So, if you will, this corresponds, of course, perfectly to that. Angular velocity is analogous to linear velocity. They're not the same, but they're analogous. They play analogous roles, different context, right? Different ways. And that's highly suggestive that this thing right here, that we entered this calculation with no plan for addressing, it just showed up in the calculation itself. I didn't do it, right? Whatever this thing is, it's the angular analog of mass. It's playing the exact same role that mass did in the kinetic energy formula. Just in an angular sense instead of in a linear sense. So that's what you want to think of this expression as being. This thing right here, you want to think of it as being an angular analog of mass. And this is the definition of something called moment of inertia. So really important physical concept, and again, this is not a physics class. The point here, though, is that this comes out of a mathematical argument. This comes out of an integration argument, Riemann sum argument, right? That makes sense out of this for us. So the general formula, integral r squared dm, where again, in general, r, that r right there just represents distance to the axis of rotation. Is everybody on board? Is that me? No? Doesn't matter. That's fine. Okay. So, now, you do have to be careful with that R. Sometimes the R is good old cylindrical coordinate R. Namely, distance from the z-axis. But that's only if you're rotating around. Oh, come on, stylus. It's only if you're rotating around the z-axis. If you are rotating around the z-axis, then yeah, cool, R is familiar. But you might not be. You might be rotating around a totally different axis. You might be rotating around the x-axis, in which case the distance to that axis, that's not square root of x squared plus y squared anymore. Now, according to the picture here, it looks like it's y. This region is entirely on the positive y side of the x-axis, but if not, it'd be absolute value of y. So different formula for a different story, all depending on what the axis is, right? And there's various different versions of this. So if you're rotating around a line like that, where x is not 0, for example, right? Well, then what's the formula for this distance? Well, I mean, it depends on that a, right? It depends on the x-coordinate of where you're at, but it also depends on that value of a, and in particular, it's the absolute value of x minus a. The picture tells all, right? So this is another one of these scenarios where you have to have a good picture to be able to make sense out of what you need to write down in a computation. So please always have a reasonably decent picture. Keep in mind as well, it's not just about your ability to get the right answer. It's also about your communication of your reasoning, right? And a picture, like if you were to draw this picture and then just write down r equals absolute value of x minus a, totally, perfectly clear, right there in the picture, no problem. Full credit. Okay. All right. So let's do one. Let's consider this area right here, where x goes from 0 to pi. And I'm going to talk about rotations around the x-axis. There's the x-axis. And I want to compute the moment of inertia. Well, moment of inertia is a pat formula that we have. It's always integral r squared dm. You just have to figure out where r is. Right? And in this situation, r, I can see it in the picture here, r is this distance right there from wherever you are, x comma y, to the nearest point on the axis. And in this case, again, sometimes the picture is really nice, and I think in this case it's pretty clear that r is just y. Is that cool? Is everybody happy? Okay, so integral r squared dm, r is y, becomes integral y squared. And then let's see here. What's the deal with the dm? Well, there's no mention of there being a density here, so we're going to assume density is 1. Mass, therefore, is area. Right? And so we've just got a double integral. And it's just a matter of computing this double integral, and you're going to notice that there is indeed also, in this case, a little bit of work to be done. You got to remember how to compute the integral of sine cubed. So I just want to remind y'all, Calc 2 is prerequisite to this course. Make sure you're good with how to do. There's a bazillion little tricks, right? Little clever little, you just have to know that little hack, that one little, right? So make sure you know all the tricks. And this is just one of many examples. Sine cubed. Here's the trick. Right. But be prepared for that. That kind of thing is fair game for the exams. Okay. Now, I am obligated also to mention a related idea called radius of gyration. I am not particularly interested in this because, yes, it is physics. Yes, it is useful in physics. This is not a physics class. How does this relate mathematically? One formula. There's no calculus in that other than calculus we've already talked about, namely moment of inertia. Yeah, sure. That part was a clever double integral argument. That was of mathematical interest here. Turning that into this thing called radius of gyration. What is radius of gyration? How do I get this formula for radius of gyration? It's all physics, not that interesting in a multivariable calculus class. So, like I say, I'm obligated to mention this because it's on the syllabus. Okay. So, so know this formula, I suppose. Okay, fine. All right. Okay. Moving along, actually, I'm going to switch over to my, I've got like 3 minutes. Okay. I'm going to move over to my 219 notes because I think these are a little cleaner. We're going to enter a new discussion for something called triple integrals. It's not that different from double integrals. Remember, where did double integrals come from? We were looking at integrals, single variable integrals. We recognize that single variable integrals are where you take an interval, a one-dimensional, on A to B on the x-axis, and we chop that up into pieces. Now, why are we chopping up intervals into pieces? Lots of reasons. Maybe there's a bunch of mass in there, or maybe there's ants crawling all over it, and I want to count the total number of ants, what have you, right? If for whatever reason you want to chop up an interval, you get a Riemann sum, which you define to be an integral. Double integrals just said, hey, let's do that same thing on a region, on a two-dimensional region. Same idea. Chop it up into little pieces. See what happens. We're going to do the same thing now with a three-dimensional region. Now, why would I want to chop up a three-dimensional region? Well, maybe there's mass distributed throughout a solid, where density is not only not constant, but depends on all three variables. Right? So a wildly non-constant density in a three-dimensional region, not a two-dimensional region. And other types of examples, if you've ever had a stat class, probability is computed with integrals, and if you have a three-dimensional random variable, so your probability density function then is a function of three variables. If you haven't taken a stat class and don't know what I'm talking about, that's fine. But the way you compute probability then would be to do an integral of this three-dimensional PDF, they call it. So, but to be able to do any of that, we have to start talking about chopping up a three-dimensional solid. And look, a lot of this is very, very similar to what we've done before. If I chop it up, I'm effectively going to be chopping up the x-axis into little pieces. We already know how to do that. We'll be chopping up the y-axis into little pieces. We already know how to do that. The only slightly new thing is that now we need to talk about chopping up the z-axis. We haven't technically done that yet, but it's morally equivalent to what we've done before on X and Y. It's still just taking it an interval of a given length, chopping into n pieces, and keeping track of where the edges are. So it's not really that new. Having done this, the idea of a Riemann sum, let me get rid of all this ugliness here. The idea of a Riemann sum is just to say, well, I've got all these little boxes that have resulted from me chopping up my big box into a bunch of little sub boxes. And on each one of these little sub boxes, for various reasons, I might want to do something like this. Now, why would I want to do such a thing? Well, maybe this is density that I'm multiplying by volume to get mass, and then I'm adding up little pieces of mass. Or maybe I've got let's say flies flying around inside of a, let's hope, contained in a little aquarium kind of a deal, right? And maybe I know population, how many flies per cubic inch that I multiply by volume. So population per unit volume times volume gives me population, and then I add up all those little populations. Whatever, right? There's a bazillion, countless applications. But this construction right here, where we say the whole is the sum of the parts, is really just like what we did with a double integral. It's just three-dimensional instead of two-dimensional. It's volume instead of area. 3 indices instead of 2. Morally, structurally, very, very similar. So this expression is hugely important. So we give it a notation, we give it a name. It's called a triple integral. I think all that notation is pretty believable. And I'm going to draw a line. So here's a piece of good news. You can get fussy about making your the way you chop up irregular instead of regular. And why do you have to always pick the bottom left corner? Why you could pick an arbitrary sample point or test point, whatever they want to call it. In this course, we're not going to worry about that at all. So any mention you see in the book of irregular partitions and such, just ignore. Not responsible for it. Okay, so what we've done is we've made a definition of something called a triple integral, and next time we'll start seeing applications and how to compute them. Y'all have a good day. See you later.